And the second one is Izuka campus for computer science. And the third is Wakamatsu campus for graduate school of life science and system engineering. So we are located here, very close to seashore. So that's why our group really like to go to beach to have a barbecue frequently. So if you want to join, please visit us anytime. I welcome. So let me start my talk. So about graphene nanoribbon. So as you know, so Moore's law. So by following Moore's law, so the device size is getting smaller and smaller, which support the development of this computer. So of course, 50 years ago, the computer was very big and slow compared from the present mobile phone like this. Mobile phone is much faster than previous old style computers. And it's because of one of the reasons is nano downscaling of devices. And if we could repeat such a downscaling, the maybe present supercomputer can be much smaller, like a mobile phone, again in 10 years, 20 years. So the device itself has a limitation, almost facing a limit of nano downscaling. But thickness of wiring, we can have some room to achieve that. So today I talk about that. So our topic is graphene nanoribbon. Graphene nanoribbon is one of the graphene, so which has similar property with graphene itself. And high carrier mobility, it's good for switching speed. So the people of graphene researcher tried to make a transistor by using this, but it was difficult because band gap equals 0. So that's a weak point. But I think this kind of graphene nanoribbon can be used as electric wiring. If we can use this graphene nanoribbon as electric wiring, so electric wire become very thin. So compared from a metallic one is around 30 nanometer in this set. But one layer graphene, single layer graphene nanoribbon has 0.3 nanometer thick. So if it's achieved, we can decrease the size of thickness of devices. So today I will talk about how to make a graphene nanoribbon from double wall carbon nanotube or single wall carbon nanotube. And we use unzipping method and to get a single layer graphene nanoribbon. And after obtaining that, we functionalize that by using some molecules, or directly we can measure the electric property from single layer graphene nanoribbon or functional by graphene nanoribbon. So this is how to fabricate single layer graphene nanoribbon. We start from double wall carbon nanotube, and we use dichloroether as a solvent and PMPV as unzipping material. And by adding together and sonicated for hours, and then centrifuge this liquid, we can get some sample. After getting this sample, supernatant was drop cast onto the mica or silicon oxide substrate, and then dry. And to remove PMPV, this material, we bake this sample at 400 degree or 450 degrees And then finally we can get single layer graphene nanoribbon sample. So this is the observation during the unzipping of carbon nanotube to get GNR. Then we start from double wall carbon nanotube. So AFM showed very round cylindrical sample like this. And we start unzipping and obtain. At first, we can get double layer graphene nanoribbon because the double wall carbon nanotube has 2 layers. Then we can get double layer graphene nanoribbon. And the AFM showed obviously we could obtain a 2-layer double layer graphene nanoribbon. And then by continuing the sonication, we could get the Y-shaped graphene. So one side of 2-layer is peeled off like this. And then finally we could get all single layer graphene nanoribbon. So AFM showed obvious graphene nanoribbon structure. And by plotting the presentation of each double row carbon nanotube, double layer graphene nanoribbon, Y-shaped graphene nanoribbon, and single layer graphene nanoribbon against the sonication time. So at first, double carbon nanotube was 100%, and of course decreasing. And final product, single layer graphene nanoribbon, is increased. And after 8 hours sonication, we could get almost 90% of graphene nanoribbon. And by using this kind of single layer graphene nanoribbon, this is an FM image of single layer graphene nanoribbon. And by using CBD method, we can increase the number of graphene nanoribbon and can be controlled. And the CPD was performed with ethanol, and the composition at 950 degrees, and the deposition at 720 to 744 degrees C. We could definitely we could observe the increased number of graphene nanoribbon, and we could control the layer number very precisely by using this method. So next, we try to find what is the mechanism of unzipping carbon nanotube. So as I told you previously, so we used unzipping method by using PMPV and the sonication. And we don't know how this PMPV works to the carbon nanotube. Maybe at first some in the reference, the people use this to avoid gathering aggregation of graphene nanoribbon, and they didn't care what's the role of this material. But I think we thought this material has some role for unzipping, so we tried to find it. And we used some variety of PMPV. This is the PMPV used, and some variety, this one, and which part of functional group is working for unzipping of carbon nanotube can be found, and we tried. And by using this for methoxyphenol, we could get this kind of material. So we use 1,4-dimethyloxybenzene could really unzip CNT. So this part of moiety is working for unzipping of graphene nanoribbon. Be found. So because in this case radical H is coming out to the solution. And in this molecule, so radical cannot coming out from the molecule to the solution. So we thought this kind of radical H plus ion is working for the unzipping of carbon nanotube to get graphene nanorobots. And the mechanism of unzipping is like this. So firstly we get we have some defect at the side wall of carbon nanotube, and this by focusing this bond, CC bond, so by vibration of sonication, this bond is disconnected and connected repeatedly. So that this so disconnected by sonication, it will be radical like this. And this is a reversible reaction, the CC bond or radical. So if the radical from H plus radical is coming from proton radical, is coming from molecule to attach here, so it's become a bonded structure and cannot reverse to the CC bonding. And then next neighbor bonding become same situation, and after vibration and coming the proton coming to this disconnected bond, so it's disconnected. And by continuing this, the unzipping is proceed. So this is a new finding from us. So next, electric property of GNR is performed. So single layer, this is a single layer of graphene nanoribbon, double layer graphene nanoribbon. So by measuring, by using AFM, the conductive AFM, we could get this kind of IV curve. And by using the DIDB method or DS, so that we could get the very close to the theoretical IV curve. So roughly we measure this kind of graphene nanoribbon conduction. So we could we proved we could get a very smooth and not damaged graphene nanoribbon was obtained. And we also can functionalize the graphene nanoribbon by using a planar molecule like this. So planar molecule can attach to the graphene nanoribbon because of pi-pi stacking. So graphene also has a pi density electron, and the planar molecule has a pi electron, and the pi-pi stacking can be obtained and easily attached to the graphene nanoribbon. And by increase the number of molecules attached adsorbed onto the graphene nanoribbon, so IV curve become from the change from the metallic one to the curvy semiconductor, semiconductor-like behavior. So by applying the adsorbing the molecule to the graphene nanoribbon, it can be controlled from the metallic to the semiconductor conduction. And the cross structure also measured. Cross structure of GNR is measured like this, and only this cross structure is connected to the electrode, only this part. And then by using the AFM conductive AFM, so we measure point by point electric properties. So where the GNR is connected directly to the electrode, we could get a metallic conduction like this, green one like this. But after beyond the cross point, it changed to the hopping conduction like this. And also crossed GNR show all point the hopping conduction, which means at the crossed point junction, there happened the hopping conduction occurred at the junction. And we also could obtain the only edge of GNR show the Schottky conduction, which means that only edge show the semiconductor on the property, because the AFM is made by platinum. So the metal semiconductor connecting, so the Schottky conduction appeared. And we tried to change the crossing angle and measure the Plato, how much is the Plato area. So by changing that, we pick up the many crossed structure and measure IV curve. And Plato width was almost constant, and 0.6 plus minus 0.2 volt here. So it was very constant. But sometimes we saw that there's no Plato area, so which means metallic conduction compared from this. And this is we thought this is because of AB stacking, like this very much matching structure of two layers. Because the two layer AB stacking make this structure, and which band structure is like this, and upper band and lower band connect at one point, and which make a metallic conduction. So we thought this the zero Plato area can be made by this AB stacking. So now we move to how to breed the graphene nanoribbon to two electrodes. So by unzipping of carbon nanotube to obtain GNR, so the final product is a mixing of GNR and carbon nanotube, or some amorphous carbon or else. So we should pick up the one only graphene nanoribbon from such a mixture to make a devices. So that we want to find how to pick up that, and we focused to the electrophoresis DEP method. So that is in the liquid we apply the AC bias, so that some attractive force or repulsion force to sample occurred because of AC. And this is a DEP force equation, but so many factor is there. And we try to find a good condition to pick up the graphene nanoribbon. And we used Raman spectra to know whether the graphene nanoribbon is breached or not. Because if carbon nanotube is breached, and by using Raman, so the carbon nanotube radial bridging mode is appeared. So if this peak is appeared around 260 to 80, so that means carbon nanotube is there. So by changing the frequency of the DEP, we could get this kind of structure, many spaghetti structure of sample. But I don't know. We don't know the graphene nanoribbon, which graphene nanoribbon or carbon nanotube breached, and we try to check what is obtained. And by changing the frequency of DEP, that we could get this kind of Raman spectra. This is the full zone of Raman spectra. And radial breeding mode is here. And this is magnified spectra around the RBM area. And only carbon nanotube is measured. It's become like this. So around 262 or 273, we have big peak of carbon nanotube. And by increasing the frequency of DEP, so up to 12 megahertz, that we could find carbon nanotube RBM. But after more than 13 megahertz, the peak from carbon nanotube disappear, which means only graphene nanoribbon is picked up by DEP method. So this is a simulation why to know why we succeeded to pick up only GNR. So in the case of the DEP force, when frequency is 0, so its dominant is obtained by conductivity here. And when frequency is infinity, so permittivity is dominant, like this. And by checking the metallic carbon nanotube, single wall carbon nanotube of the conductivity and permittivity, or single layer graphene nanoribbons one, and dichloroethan solvent one. So by using these values, so we calculate the DEP force. So we found, the DEP force is like this. So we found around 10 to around 10 megahertz. So the DEP force, this is the attractive force. The upper is attractive force. So the sample is closing to the electrode. So the attractive force is crossover at some 10 hertz, 10 megahertz here. And this is magnified graph of this. And at the 34.7 megahertz, so the value of DP force is crossover. So more than, which means more than 10, around 34.7 megahertz, so only graphene nanoribbon will be picked up by using the DEP method. So this is this is a very good coincidence to the experimental. So this is very rough, because this calculation is very rough, but still the order is the same with the experimental data, so more than 30 megahertz. So this is the conclusion. So by unzip of single wall carbon nanotube or double wall carbon nanotube, single layer graphene nanoribbon was obtained. And layer number of graphene nanoribbon was controlled by CVD precisely. Electric property of single layer graphene nanoribbon was investigated. And electric property of single layer graphene nanoribbon pre-molecule complex was investigated. And unzipping of carbon nanotube mechanism was proved. And GNR graphene nanoribbon pickup by electrophoresis was succeeded. So this work is done from my group members. So we have in my group I have many foreign students and supported by many scholarships. So I really would like to thank to the scholarship and the budget support. Thank you very much. That's all.
So can you tell anything about the age type? zigzag or armchair or the direction of unzipping, can you control it?
Using this method, but by observing STM, so only zigzag structure is obtained, we guess. And some molecule is attached to the edge because we are using the molecule for unzipping, and not only H proton, but also some other molecule attached to the directly to the edge of graphene nanoribbon.
Excuse me. During what about chemical unzipping of your nanotubes? Yes, nanotubes. How you can control the edges of obtained graphene nanoribbons? Because during such kind of procedure, yes, you will have hydrogen as far as I understood. You will have hydrogen terminating boundaries, yes, but it's maybe not perfectly correct because chemical unzipping leads to chemical modification of the age boundaries of these nanotubes. And what about the rectangular form of nanotube? If you have obtained nanoribbons, if it has some another form, yes, you will have big problem with electric and magnetic properties. No, like graphene nanoflakes, for example. It's a known problem, actually. What can I say about this method? Because your nanotube, according to chemical unzipping, your nanoribbons may have different vacancy, different defects, and so on the boundary. So each state should be present, yes? But no.
By checking from AFM or other Raman or some other method, our graphene nanoribbon almost has no defect. And this is because if there's defect, it's easily decomposed to the flake. And if the nanotube alive, so there shouldn't be defect in the nanoribbons. So that's why we could get a very no defect carbon nanotube from that.
Okay, thank you very much.